Boop, boop, boop. Okay, I think I'm ready. Morning, folks. Sorry, I'm just a little bit slow getting started here. Dora and I just walked in the door. Okay, do that later. All right. Morning, Dora. Dora's right here beside me. Uh, it's super cold outdoors and a lot of wind. Winter's here. uh, I'm not ready for this. I don't know about you. Many of you I know live in warmer climates. It's just, I grew up in Montreal where it was very, very cold, but I can't handle this anymore. Hmm. Okay. So, before I get started, um, that we've got, um, I've got marking get done this week. Whole flurry of late assignments and makeup tests and all that sort of thing have been flying in. That's what I'm just doing now. I print them off and I just have trouble marking online. I had trouble getting used to it. Anyway, but we're coming quickly to the close in the course, surprisingly. And we don't have a lot of big items left. That about 20 points or so in the course still might remain. That we've got test 5, our last test, is going to be on Friday. It's on chapters 9 and 10. Again, it'll look like quiz questions from 9 and 10. I expect that although I try to keep the quizzes about half and half on the 2 chapters, I expect this one will be probably 2/3, probably 12 out of 18 questions will have to do with probability. And they'll look like the ones in the quiz, the ones you just had in your assignment, that they, uh, if you need extra problems or practice ones, I could probably post some of those because these are all manual that you do, and I'll try to keep the numbers reasonably straightforward. Um, and we'll only have maybe 6 questions out of the stuff I'm going to zip through today. And I'll try my best again at trying to lighten up my tests. They've been too hard, and I keep saying I'm going to try to make them easier, but I've so far not been very successful. This one should be the probability stuff should be very straightforward. It'll be a probability table and a bunch of things like you've got in your current assignment. Then there'll be a probability tree that for you to do. And again, maybe I'll see if I can't. Um, I've got lots of solved problems there that I could probably post for you. That they, I've got one assignment left to make up, and no, there's no final exam. We have no final, um, and that's the whole idea here. That I decided a year ago that this course doesn't lend itself well to a final exam. And looking at courses I've taught in the past anyway, I think I've had it with finals. Uh, that's why we've got that series of 5 tests, and we got the quizzes. That's more than enough testing on you. Right? Final exams are not particularly productive. And with doing things online, which was a different issue altogether, that high stakes, high risk, big point value examinations, uh, are tricky to do in an online world. Uh, so many things can go wrong. But in particular, we can have a secure exam environment as much as people try to do that. And the security types of features that people have tried putting in place for finals, I think, harm the students more than protect the exam. So that's why I've shifted to all low stakes for smaller activities, at least. But so we've got the last test, and we've got quiz on chapter 11 coming up Saturday, and then there'll only be a quiz on chapter 12, and that's it for testing. I've got one more assignment to make up. We don't have material that really makes a big assignment, so it'll probably be, again, some probability stuff. Um, Probably should have that type of no. Anyway, it's not going to be a lot on it because most of the stuff we've got left, I'm not going to have you do manually. The very last material in the course is about how to create good charts and communicate stuff effectively. But I want the assignment done before we've even done that, actually. We want to wrap things up by the end of classes. And you've got other courses, you've got other work to get done. I've got enough, or will definitely have enough to be able to evaluate you in the course. So, I think that's it in terms of covering off those sorts of issues. Anyway, uh, no further ado, unless you've got questions on things. Um, we'll start in. This is from the weekend, Dora and I at Frog Pond. That it was late in the day, getting the last of the sun coming through the trees at her. Yeah, big long shadows you can probably see in the background. And uh, this was yesterday morning. An ugly, dark day morning. Yesterday was just not a nice day. And so Dora, after she came in, just curled up, and Bruce was already curled up. And that's where they spent most of the day. That I am going to backtrack and talk a little bit about uh, probability and probability trees, sort of recap that. Uh, but in part, it's because there are two things associated with that conditional probability in the trees that suggest alternate ways of doing some classification. And classification we've not done as a topic area like we did with regression and doing it with, with Excel, value estimation, that type of thing. The tools for classification that I can't easily build them in Excel. And I'm not sure if there's much to learn from it. I'd like doing value estimation because it was one topic we went into a lot of depth on, maybe a little bit too much for you for a first year class. But the what I like about classification is the wide variety of different ways people have thought of to try to do classification problems. And they've shown a lot of imagination, different approaches we can take. And that too often in your uh, courses in finance, accounting, quants, and the like, they always seem to have one way to do things. We don't have one way. We got many, many, many different ways to do things. And that's classification is a particularly rich topic. So back up. Conditional probabilities are about uh, chance of one thing happen given something else has happened. So there's a sequence. One happened, then the other one is. And we can think of a whole sequence, not just two things, but A, then B, then C, then D, and so on. And the and having conditional probabilities as each step in that chain. And trees are a nice way of trying to explore all of those different possible outcomes because there becomes a lot of variety as you branch out in that tree. That the trunk of a tree is one big fat guy. But when you look at all the little tiny branches that are at the end. There's millions of them. So there's so many different outcomes you can get at the end, and it's hard to organize that information uh, and process it all. But the tree helps. The tree is a conditional thing because you can't travel along a branch and get to the end of it if you haven't started on that branch. And as you're traveling along the branch, you get other branches that travel, and you can travel along them. So the chance of going along a branch depends upon how you got there, and depends upon where you are in particular before you can branch. And uh, implicitly, when we work through this tree, we are doing a variety of calculations and applying formulas, but we aren't explicitly looking at them. Yes, I got your assignment. I've got it actually right in front of me. But I'll get back to people. If I'm missing anything, I'm going to hound you. I don't want anybody having any missed quizzes, tests, or assignments that you're throwing away points if you do. So I will be chasing after people with gaps. So the trouble with probabilities, though, uh, even with trees, is that they aren't that intuitive. We don't have a very good feel for the size of the numbers, where these formulas come from, how they work together. They just aren't intuitive. Most people, it doesn't come naturally. They find probability very frustrating. Uh, and unfortunately, the way probability is taught in many introductory courses uh, at high school level and at university treats it as a bunch of puzzles. And most of us hate trying to work through these puzzles. They get frustrating. And then there's this dirty little trick that lets you solve it. That's not, it doesn't work for me. That, but if you've got frequency data and you've got information organized in that fashion, people can often work out relative frequencies that they can calculate probabilities if they can see those objects. And I think it's a part of visualization of this that probabilities are too abstract, but if I convert it into people or objects or things I can see, then it's easier to think through uh, how it goes. So um, the example I did last time had to do with a rapid test for COVID. And if you read in the paper, or at least yesterday morning's paper, I didn't know Nova Scotia was using rapid tests yet, but they had a pop-up COVID test center downtown on the weekend, and outside of the dome. It's, if you don't know the dome, it's, I've never been in there, but it's a bar, very popular bar in downtown Halifax, and they did rapid testing down there first of staff, make sure that they were okay, that were working in the bar, but then they started testing patrons that were going in, and they actually found one positive test. Um, that since it's not all that reliable to test, that the individual, he was then taken off and administered the full nasal swab type of thing. I don't know what the results were of that, but we've had a lot of cases in Halifax. So anyway, the way we could work through this tree and the way it's easier to visualize these ones is when you're given a bunch of probabilities, maybe turn that into people or objects, things. So with this, I'm testing people, so I'll convert it to 100,000 people. And if I've got 100,000 people and 1% of them are supposed to have COVID, then that would be 1,000, 1 in 100. And so 99,000 would not have COVID. So I take my 100,000 and I split them. So this idea of splitting individuals or observations into two groups, that the 1,000 COVID ones and the 99,000 non-COVID ones. Where did we get it from? We just multiplied a percentage times the number of people we started with. And we could do that again. If you've got COVID, the chance of a positive test was said to be 97%. So that we could branch this way here. Well, 97% of 1,000 is 971. And that leaves me 2.9% that get a negative test result. That would be 29 people. So these, just for a bit of language, these are false negatives that the person really does have the disease, but we accidentally diagnose them as being negative. Okay? Um, that now, with those that don't have COVID, we don't know that. That's why we're administering the test. 98.5% of the time, it should come back negative. Great. But 1.5% of the time, we will get a false positive. Someone will get a positive test, but they really don't have the disease. And when you multiply it through, that seems like a small percentage, but a small percentage of a very big number. We see that's 1,485. That's a lot of people. And yes, it gives the right answer very frequently to 97,515. And these are my various outcomes. And seeing these as people helps me get a sense of, do I get false positives or false negatives very often? And I get a few false negatives, but I got a huge number of false positives. Actually, more false positives than true positives. So I'm making a lot of mistakes. The And we've applied a formula in doing this, a multiplication formula for conditional probabilities, but we haven't really seen a formula. We've just used common sense and reasoning it out. And if these positive test people are given another test, then we could keep going and keep branching. We don't have to just do it at two levels like this. We could go and have 3 events or 5 events or as many as you like. Trees were nice in terms of exploring all these options. And then our other thing is to go and look at summarizing it, to put it in, because if I've got a lot of branches, it gets really busy, very complicated. And once I got it in a table, most students can give me an answer very quickly. If I want to know you've got a positive test result, what's the probability you have COVID? Well, I had 2,456 positives. It's a large number, but only 971 were COVID. So my answer is 40%. And I can reason this out. So it's okay. It's more likely that you don't have it than you do if you get a positive test. At the moment, I was listening to, it was on the national news last night, Lisa Barrett, who's an epidemiologist at Dalhousie. And she was talking about these tests and saying, okay, you get an awful lot of false positives. But if I've got to make 2 mistakes, if I get a false positive, then I'll go on, I'll do more testing. When I get a positive with these rapid tests, because I know they're not super reliable. And that's great. And I'll get to the bottom of things and I'll know if the person has COVID and we've just got to stop the spread. That I'd rather make a huge number of false positive mistakes than to make any false negative mistakes, because those 29 false negatives here are people with the disease that are running around infecting other people. And so those 2 errors, and we'll talk about that on Thursday's class, the false negatives may be far, far more important mistakes than those false positives. But these things, again, they help us understand what's going on. So what do I get out of all of this? That there was that way that I looked at it, where I was using a tree and splitting and splitting and splitting people up into different groups. Or I could have done this right from the start and used a formula, and that was called Bayes' rule. And that formula is overwhelming, intimidating. I'd probably want to just stay away from it. But what we're going to look at today are 2 methods for doing classification. One of them that's based upon trying to simplify Bayes' rule, and the other one is this idea of splitting and carving them up into different groups. So our goal is always a conditional probability. Well, even better than a probability. We'd like it to be a certainty, not a chance. That if I was looking at customers I've got and whether or not they're going to renew their insurance policies, because I make more money off of the renewal the first time round. There was a lot of work involved and cost in getting that first customer. But once I've got them, I want them to renew their policy. That's where all my profits will come from. And uh, I'd like to know who is likely to renew their policy and who is not likely. That with the ones that are likely to renew, that's important because I don't want to do anything that loses them. They're my customers to lose because they're more than likely going to renew unless I do something stupid or something happens. I got to make sure I keep those. And the ones that I don't think are going to renew, maybe there are nudges or incentives I can get them to make a renewal. So what I need to know is, can I identify customers likely to renew and those not likely to renew? Ideally, I'd like to have the probabilities, these conditional probabilities, close to 0 or 1. So can I define one market segment, one group of customers where it's almost guaranteed they're going to renew? That's great. And as many of those groups as I can. And then I'd like to segment them into that other group where they are likely not going to renew. And maybe I shouldn't waste my time on them. That um, I'd like, I don't like probabilities of 0.5 because then I have to make a decision. I like probabilities that are close to 1, close to 0. How do I try to find a way of getting that probability to move either up to 1 or down to 0? Well, um, that, no, I'm talking about branching like I just did. This is a useless slide. I probably should delete it. That, um, but when we did the branching in that, and then we summarized, and it was to flip things around. So going from one type of information to another and working backwards. And that the branching helped us, and because it split our customers into different little groups. So what we could do is look at uh, characteristics of our customers, simple ones like what's their gender? Are they male or female customers? And are males and females different with respect to renewal? If they're not different, then I don't care. It's no help to me. It doesn't take me any further ahead. But if, say, females were more likely to renew and males less likely, then that's useful information. If I looked at their age, and maybe I was looking at males, and so imagine me going down a tree and I'm looking down the male branch of the tree and then looking, okay, among the males, let's look at those that are over 50 and those that are under 50. So I'm taking a numeric variable and I'm splitting it into categories. And that, and if the ones over 50 are more likely to renew, oh, okay, males generally don't, but if you're over 50, maybe you do. But if you're under 50, maybe you don't. And that gets further refinement there. Um, with those over 50, should I look at their accident record? Have they filed claims because they were in a car accident? And does that affect whether or not they're going to renew? I've got lots of data. I know where they live. I know how long they've been with my company. I've got all of their history. I know what car they drive, the age of their car. Uh, do they carry house insurance with me and other types of things? Are they seemingly careful people? I got lots of stuff. I could build a great, great big tree. That how's that help me? Well, um, we're going to look at sort of like probability trees. They look almost like them, but they're what we'd call decision trees. So I'm looking at branches of the tree, and the tree is going to have at the end of a branch some people that have COVID and some people that don't. Maybe they're a mixture of people, but I'm going to try to split them into groups where my groups are. You hear people talk of they're clean groups. They're all the same, or they're pure groups. They're pure in that there's no impurities, there's no contamination. That everybody in the group renews their insurance. Everybody in that group doesn't renew their insurance. That and then I'm going to use that information. So what I want to do is start out with all my customers. That's at the root. That's the base of my tree. And then I'm going to branch them into two groups, subgroups. And I want them to look as different as possible with respect to the outcome that I'm studying. And so these new groups that I've got are my decision nodes. I'm going to look at then branching from them again, and I'll keep branching and branching. And somewhere along the way, I'm going to decide I better stop branching, that I don't want to go on forever because I may have an awful lot of information. So easiest to do, this may not make sense to you, so let's work through an example. So let's suppose I've got 100 customers. Uh, you know, imagine a bigger number, but let's start with just imagining 100 because I want a simple number to work with. And let's suppose 60% of them renew their insurance and 40% do not renew. So out of 100, that would be 60 renew, 40 do not. Okay. And maybe I decide to look at gender. And are female customers different from male customers? Well, I'm starting out with 60% of my customers renewing. It's that sort of middle, muddy probability, hard to work with. But when I look at females, out of the 50 females, 40 of them renewed. So that's 80% renewed. So among females, 80% renewed. What about males? Well, out of the 50 males, only 20 renewed, or 40%. So for females, it's 80. For males, it's 40. Those are two very different probabilities. One of them is moving closer to 1, which I'd like to see. The other one's moving closer to 0, which is, yeah, not great because I don't like them. I'd like them to renew, but it means they're very different. So I've separated the two, that I've discriminated between two groups of customers based upon gender. So let's look at the males. 40% renewing. It's a muddy number that's in the middle. Uh, can I differentiate them a little bit more? So suppose I look at age, and suppose I've got 20 customers that are over 50 and 30 that are under 50. Among the 20 that are over 50, 15 of them renewed their policies. 15 out of 20, that's 75% renewed. Oh, that's a much higher renewal rate. What about those under 50? Well, only 5 of them renewed. So I've split them up, and of that 20 that renewed, 15 of them were over 50 and 5 of them were under 50. And of the ones that didn't renew, the 30, only 5 of them were over 50, but 25 of them were under 50. So the renewal rate among males under 50 is only 20%. But of those over 50, it's 75%. Again, here are two probabilities. One's pushing towards 1, the other one pushing towards 0. This age seems to discriminate among them. I could go down further and look at the ones over 50 if they had an accident. And now it's interesting. These last two I've got here, these are what I call clean or pure nodes. Those that had an accident, none of them renewed. They're all the same. Those that had no accident, they all renewed. They're all the same. So these are those ideal ones so if I had worked out what's the probability of a male over 50 that had no accident renewing, I'm going to get 1. And if I looked at the probability of a male over 50 that had an accident renewing, I'm going to get 0. So these two things, this is the ideal that I'd like to head towards. And so I keep looking. Sometimes I may not be very successful. With females, I got one group that was very clean. They were married. Single ones, I'm back to having something that's messy again. It's still almost 50%. Um, so, but maybe I take this group and I can subdivide, but I've pulled off one group here that's almost clean. They're almost all the same. Here I got a group over here of males under 50. They're almost all the same. Maybe a little bit more refinement, and I can get them into nice clean groups. So when I'm finished, I've sort of already alluded to this, I, I can come up with a set of decision rules that work most of the time. If a customer is male over 50 with no accidents, this customer will renew. Female single under 30, no accidents, this one is probably going to switch. And I got many, 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 many different rules because of all of these different possible things at the ends of my tree. Every terminal node, every ending point on my tree, like a leaf at the end of the tree, had a path. And I have to describe that whole path to describe the people at the very end of the tree. And but it's it, it's just a lot of rules, and really they're relatively easy to understand. It's easy to give someone instructions. You give them a checklist. Go through this checklist, and if they it's this, then this will happen. If it's that, then that'll happen. There's not any fancy theory here. I haven't tried to explain why males or females are different, why older, younger customers are different. I'm not concerned about that. What I'm concerned about is coming up with some type of rule that works. Generally, outliers, other types of data problems, they don't seem to bother me either. This is really nice, simple. So I just need a couple of things though. How do I decide how to split? And how do I decide when to stop? And that I did it by working out a couple of probabilities. And so with the males and females, I got this 80%, 40%, very different. So I split on that. And on age, I got 75% and 20%, very different. So I split on that. So I tried to calculate a branching so that the two branches had very different probabilities of ending up at the end of those two branches. And in that sense, I'm discriminating between customers that renew and those that don't renew. Uh, I use probabilities because that's what we've been doing for the last week. Uh, and it seems intuitive. It seems to make sense. Um, but I'm not aware of anybody that uses that approach. And they use other ones that they come up with, which are similar. They're ones that discriminate. And there's a whole bunch of them. I'm not going to go into the math behind each of them. But they are splitting strategies that somehow discriminate between two outcomes. If you were to uh, read articles or in the business press and that sort of thing, they may talk about how they work. A lot of these are built into software that you can purchase for doing data mining. There's the three that I've run across that seem to be the most common are called Gini, one called Entropy, and one called chi-square. And Gini is used in, more often I don't see them talking about Gini, but they talk about a thing called CART, which is a particular technique for doing branching that along the way uses this Gini idea for doing the splitting and picks variables to split on that will discriminate as much as possible. And if it's a continuous variable like age, it's not just picking age, but should I split at 50 or should I split at 40 or 22 or 65? And within that method, you would be looking within CART, looking at where to make that cut. And as I said, it's used in a lot of different pieces of data mining software. That chi-square is one that you will see that term come up, and actually the method indirectly when you take statistics and they look at things. We've been calling them contingency tables, little probability tables. It's used for studying patterns in contingency tables. And that particular technique that was used in statistics has been sort of hijacked, and it's used in a method called CHAID, CHAID. And CHAID is, some may run into it if you uh, have opportunity to use Watson. And I believe one time anyway, you could use Watson for free, an educational version. You may want to Google it if you're interested in data mining. And it's sold by IBM and SPSS, and it's their artificial intelligence software that it's supposed to be very successful. I hear it being promoted all the time. I played with it once a few years ago, but I really don't know too much about it, other than I went looking under the box, under the hood to see how does it work, and discovered, oh, it used Shade. Some reasonable logic there. And it will automatically build your decision tree for you. Entropy, um, I get a kick out of it because it's based upon the second law of thermodynamics. I think that has to do with um, the way um, things tend to fall apart, or it's hard to keep stuff together. You need energy or something to keep something intact. I can't exactly remember all of it. I never studied engineering, um, but it's used in information theory. And again, that goes back a long time ago. Uh, it's just another method that each one, and they give similar results, but they are just numbers that if the measure is bigger, then there's more difference. And if the number is smaller, then there's less difference. And we're trying to find things that create big differences, big discrimination. And all three of them seem to work equally well, is the case with a lot of the classification tools. They all work about the same. Um, but these decision trees are problematic. So you've got, uh, you need a rule for splitting, and there are many of them out there. But if you can recall, this is sort of what we were doing when we did pivot tables. When we take a pivot table and we'd look at one variable and then we'd have another one. And so we'd look at the pattern in here, and then we might split it down lower, or we might filter and get down smaller and into smaller and smaller groups. In assignment 2, you looked at the incidence of depression among males and females and whether they were domestic or international, I think. Or no, 2019 versus 2020. I don't, there were a bunch of different variables. We could go and drill down in that one. But the trouble was we ran out of data. Our sample sizes got too small, and any estimates you'd get would be awful. So generally, we don't want the subgroups to get tiny. So we might have a stopping rule that says once we get down to a group that's less than 50, no more splitting. Can't split a group that's smaller than 50. 50 is the smallest group you can split. Or you may even put a higher threshold. Depends upon how much data you've got. But some of our data sets, we've got millions, billions of data points, huge, huge, massive amounts of data. And so we're not going to run out of it quickly. But we may end up getting a tree that's just way too complex. We've gone down that 10 levels, 20 levels, or something like that. If you go down 10 levels on every sort of branch, you'll have 1,000 different rules you're going to end up needing at the very end to describe everything. That we say that if you drill down too far, you risk overfitting. If I wasn't worried about sample size, I could split customers right down till I have, okay, I have one customer that renewed, and this is a description of that customer that makes that customer unique. And here's another customer that's unique that didn't renew, and here's a description of that one. And so at the end of my tree, I might have, they're pure nodes at the end because there's only one person in each one. But the trouble is it describes that data set perfectly. It describes every customer that renewed and didn't renew and gives a full description on each one of them. But if I go and try to apply that set of rules to a new data set that I've never seen, it probably won't work because I've customized it and tailored it so well to this data set I did the training on that it doesn't apply to elsewhere. I can't generalize it. And we call that overfitting, that you fuss too much to make it match perfectly for this data set and give perfect answers for this data set, but then can't use it for other data sets. So uh, overfitting is a real risk that we run into. Generally, it happens when you get down to very, very small groups, or sometimes your decision rules are just way too complex. So you need a stopping rule so that you don't go too far in doing your analysis. So again, just to recap here, it's a sequential way of splitting, sort of using this tree idea that we had. Ideal is to segregate the data into very pure, clean clusters that where all the members of a cluster are really the same. And then that description of the cluster is like a set of rules. And that if you've got A and B and C and D, then the outcome is going to be Y. And there are many different strategies for splitting out there um, that we have to worry that in large data sets that we don't split too many times and make our rules too complicated. But the logic in it seems nice. Um, Overfitting can happen, but we can be careful about that. Um, some suggest after you've done a lot of splitting, you may go and decide, can I prune backwards? Can I trim the tree a little bit without and make my rules simpler without losing too much? Sort of like in regression analysis, after I've added too many variables, maybe I should throw some back out again. And it's the same idea here, that we could move backwards. And but they're very popular. They're very easy to implement. They're very easy to explain, and they generally work quite well. They work just as well as the other methods that we've looked at before. So that's one route where it uses that idea of splitting in trees. The other is to go and look at that formula that we've got, Bayes' rule. And we're still trying to get a probability that's really close to 0 or really close to 1. Okay, those are the ideals. So, and Bayes' rule flips from probability A given B to probability B given A. So if I've got all my customers there, I've put them in two piles. Here's all those that renewed their insurance. Here's all the ones that didn't renew. What do the ones that renewed their insurance look like? What information do I have about them? What do the ones that didn't renew their insurance, what did they look like? Okay. So I've got those two pieces. And now can I flip that around using Bayes' rule? And if I've got a customer in front of me that I've got the description on that customer, can I then decide, are they going to be in the renew group or the not renew group? Which group are they going to fit into? And that idea of flipping is what Bayes' rule is about. But Bayes' rule is really complicated. That the simplest sort of format for it is the math I've written up there, where it takes A given B and flips, well, starts with B given A and flips to A given B, but does it by taking this term and then multiplying by probability of A and dividing by probability of B. So what does that look like? If I wanted the probability to renew, given you're a male over 50 with no accidents, have those three characteristics, as a probability statement, I'd need to know among those that renew, what proportion are male over 50 with no accidents? And then how often do my customers renew? And how often do I get males over 50 with no accidents? So I need all of these pieces together. To calculate some of these without getting into tiny, tiny samples is challenging. That, I can work out those proportions. But suppose I've got 10 customer characteristics Well, that's splitting my customers 1,000 different ways if I do a two-way split. And even with 50,000 data points, that would give me 1,000 groups of 50, which is the smallest size I want. But that's going to be on average. I'm probably going to have some groups still that are several hundred and some that might be only 3 or none at all. I'd probably need 500,000, 1,000,000, 2,000,000 customers to be able to split that much and not get into problems with tiny samples. This isn't going to work doing it that way. There are other approaches that involve further exploration of those probabilities, but what happens is we run into interrelationships among the variables that um, we're looking at gender, age, accident rates, and they may be interrelated. That accident rates for those under 50 might be different for males or females, or they're interconnections between these. They're not independent of each other. It's like in regression analysis where in predicting a house price, if the house is bigger, has more floor space, it's probably on a bigger piece of land, probably has more bathrooms, might well have a garage because it's an expensive house. There are a whole bunch of things associated with it that they're interconnected. If I've got one of them, I probably have some of the other things there. Same thing happens here. That if you remember from probability of previous class, I said if they're independent, it means they're not interconnected. They're not related. It means in regression that we don't have multiclinearity. That so what would happen if we just assumed everything was fine, that they were unconnected, they were independent? Um, it's not um, the assumption is probably false. But what would happen if we made that assumption? And how would it change the way we would do our calculations? And this simplification thing takes that probability that I had up there and it splits it up into a number of little ones. Now, this may look just as bad to you, but look at it. I look at what proportion of those that renew are male. So among those that renew, what proportion are male? Well, how does that compare to my customers in general? What proportion of all my customers are male? Are there are they are males more common among those that renew or among the general population? How about those over 50? Um, what proportion of my customers are over 50? And among those that renew, what proportion are over 50? And so are the older people more common among the renewals or are they less common among the renewals? Same thing with accidents. Are they more common among the renewals or less common? That these things are actually very simple to calculate, each one separately. Notice here I'm looking at all my customers. Even if I had 10,000 customers, this is a proportion out of 10,000. And if 5,000 of my customers renewed, I'm looking at males out of a group of 5,000. So my sample sizes are big to work these out. And same with all the others. And then in the end, I tack on the chance what proportion of my customers renew. That this very often results in a number that isn't that accurate. It doesn't calculate the probability precisely. It may give us 9% instead of 15%, or it may give us 70% instead of 85%. But if I look at customers where the numbers come out really low, they don't renew. Those that where the numbers, the probability thing comes out fairly high, they are likely to renew. So it actually is quite good in discriminating between those that renew and those that don't. Um, that And these ratios here that I've got, each one of these little ratios I've got, it's saying, are males more common among those that renew or less common among those that renew? If they're more common than among those that renew, then it means males are more likely to renew. If they're less common, then it suggests males are less likely to renew. That ratio gives me insight about each one. Ratios that are bigger than 1 increase my probability, and ratios that are less than 1 will reduce my probability. And I'm going to multiply all these together. So if I got a whole bunch of them that are bigger than 1, it's going to drive my numbers up. If I have many of them that are less than 1, it's going to drive them down. So what's that cluster of ones that bring it down? What's the cluster that takes it up? And those ratios are called lift, is the term that's generally applied. And that if you've got a lift that's bigger than 1, it means it's going to increase the probability, increase the likelihood. And if the lift is less than 1, it's going to reduce the likelihood that it's going to happen. That and just by looking at lift, then I can start looking at what factors. It's sort of like in a regression formula, things that have a positive coefficient and ones that have a negative one. Positive coefficients increase the house price, negative coefficients decrease the house price. Same thing is happening here with lift. Lift's bigger than 1, increase the probability, increase the likelihood. Less than 1, reduce it. That the method, because we're making this very extreme simplifying assumption, we call it naive. Someone that's naive is someone that has very little experience, very little knowledge. They're making very simplistic decisions. And they call this method naive Bayes. And it's been remarkable that it actually works very well. That not in estimating the target probabilities, but in differentiating between um, those likely and those unlikely to renew their insurance. And lift is often something that's very easy to calculate. I think in the chapter uh, 10 that I make reference to an article that came out a few years back where an experiment was done where a bunch of Facebook users were asked to do a simple online IQ test and to try to estimate their intelligence. And they were then asked, would they allow access to their Facebook profile to see their likes? What do they like? What do they don't like? What types of shows do they like? What books do they like? What movies do they like? What music do they like? And then they built a classification model uh, that used Lyft in a sense to do it. And they found that uh, if you watch certain shows, you were more likely to have a high IQ. And if you watched other ones, you're more likely to have a low IQ. The article didn't tell us about the low ones. They told us about some of the ones that seemed to increase the IQ. But that became scary because, okay, they did it on this study of several thousand volunteers, but they could then turn around and generalize that to look at Facebook customers generally. And uh, it showed an example of how Facebook can learn a huge amount about you by looking at some of the things you do on Facebook and then looking at lift associated with some outcome they want to measure. And that, so if there's something that you didn't tell them, you didn't tell them your sexual orientation, they can guess it out of your profile that's there. You didn't tell them your gender, they can guess it. They didn't tell you different types of things about yourself. They may be able to guess your age, your occupation, all kinds of different sorts of things, just by looking at these lift measures. So anyway, that takes me to the end for today. We looked at now 5 different approaches to classification, and they're very different from each other. One of them estimated a probability using a regression type formula, an S-shaped curve, that then we'd need a decision rule to tell us, okay, when should we say yes and when should we say no? K nearest neighbor said, let's look at 7 people that look like you and see what they did. And what the majority of them did, that's what we think you're going to do. And it's sort of like working from experience. How did I handle previous situations like this? And what things worked and what didn't work? Same idea. Discriminant functions uh, is another one that likes the idea of a formula. Can I come up with a formula that describes a fence? And if you're on one side of the fence, you're good. And if you're on the other side of the fence, you're bad. And I can discriminate in that fashion. And there are different techniques for trying to figure out how to build that fence. Decision tree is the idea of just let's split people into different groups until we can come up with these decision rules that say if you're this and this and this and this, then you're that type. And if you're that and that and that, you're this type. And naive Bayes goes back similar to sort of logistic regression of trying to score cases as to whether or not they're good or bad, and uses a very simplistic approach to do it. It's very easy to implement, um, and it seems to work a lot of the time. And there are a lot of other methods as well. There isn't one best one. I keep returning to this. They all have strengths and weaknesses to them. That it may be your data set is more suited to one method than another, just because of the structure of it or the nature of the data you've got. So if you've got access to the software, you might want to try several different methods and decide which one is best and which one seems to give you the right answer the most often. And maybe it goes back to that issue of false positives and false negatives. Maybe it's the one that gives you the smallest incidence of false negatives because that's what you're most worried about. What are the consequences? And what do we mean by best? Because all of these methods make mistakes. So that's what we're getting into next. How do we do evaluation of what is a good outcome and a bad or good performance and bad performance when we're looking at classification? It's quite different from looking at regression analysis and measuring the quality of our model by looking at standard error or prediction errors. These are different type of errors and different types of consequences. So that's what's coming up next. And we're almost at the end. Anyway, that's it for today. I don't have anything further to add. You'll see me again on Thursday. If you've got questions on anything, don't hesitate to get in touch. I will try to get onto getting my marking done as quickly as I can, as well as I've got to get that last assignment ready for you soon so that you can look at trying to wrap up this course and allow you to focus on your other courses. Okay. So you take care. We've got some sunshine out here now. Still cold and windy, but maybe it's a nicer day than it was first thing this morning. Bye now.